The astrolabe is a very old scientific instrument. It is a measurement device and a calculator. You can use an astrolabe to measure the altitude of a celestial body, to calculate its rising time, assess to the angle between two geodesic points on Earth, or convert coordinates of a star from the equatorial to the horizontal system. The astrolabe has a clever design that involves many calculations, which was a challenge considering that everything had to be done by hand. Making an astrolabe requires many crafting skills such as metal cutting, engraving, following precisely the layout that has many curves and lines. The study of astrolabes allows you to consider various disciplines such as geometry, astronomy, history of sciences, navigation, crafting techniques, and more. Let's start this exploration of astrolabes with an expedition sponsored by King Louis XIV of France, in 1785, in order to explore the southern seas. The leadership of this expedition was given to Jean-François de Galaup, Count of La Pérouse, a famous explorer. During 3 years, the two ships will explore the coasts of South America, sail past Cape Horn, stop at Easter Island, head north up to Alaska, cross the Pacific Ocean to Japan, Korea and Australia, to finally sink next to the coasts of Vanikoro in the Samoa archipelago during a huge storm. The crew will eventually be massacred by the local population when they tried to reach the coast in longboats. The two boats of La Pérouse's fleet were named after the two most important scientific instruments for a sailor at that time: la boussole, which is a compass, and l'astrolabe. The compass used on boats gives the direction of the magnetic north and makes it possible to keep track of the position on a map. The kind of astrolabe used on boats is called mariner's astrolabe. It is a very simple version used to measure angles, mainly the altitude of bright stars, to assess the latitude. The mariner's astrolabe will be replaced years later by sextants, invented during the 18th century and more adapted to catch the altitude of the sun. To these two instruments, we need to add the marine chronometer, that made possible to detect the time shift of an astronomical event between the observation site and a planned schedule for known locations on coasts. This time shift was converted to longitude and allowed the sailors to precisely place the ship on a map, not only in latitude but also in longitude. The mariner's astrolabe is composed of a disc, engraved with angles around its limb, and a rotating alidade that can point to a star. A ring on top allows the user to suspend it vertically. The disc is open to reduce its resistance to winds. The bottom has a stabilizing mass to keep it still during the measurement. These astrolabes were usually made in brass or bronze to avoid oxidation and rust. Their thickness was usually at least 1 centimeter to avoid deformation and twist due to humidity and temperature changes. But the consequence was the weight of these instruments and their high price. Here, an example of a mariner's astrolabe drawn with the Shadows software. Due to its simplicity, making such an astrolabe is quite easy. Here, an illustration of how a mariner's astrolabe was used to measure the altitude of a star with respect to the horizontal plane. The astrolabe could also be used horizontally, for example, to measure the angular distance between two peaks of a landscape, seen from the sea. It was a useful tool to draw a map of newly discovered coasts and territories. Many different types of astrolabes exist, besides mariner's astrolabes. For example, the planispheric astrolabe is very rich in its layout and a real masterpiece. We will study it later in this presentation. The quadrant astrolabe, made of a quarter of a circle, provides the same service as a larger astrolabe but using a quarter of its surface. It is therefore lighter and cheaper. Or it offers a higher resolution for the same weight. Universal astrolabes exist in several variants. Their innovation was to be latitude independent, and therefore usable everywhere on Earth. We can estimate that the first astrolabe was made 2,500 years ago, although no clear inventor can be identified. We can distinguish three periods. The first one, that I call the pioneers, spans over 5 centuries, during the ancient world, between Greece and Egypt. 3 well-known authors established the mathematical and geometrical basis of the astrolabe. Ptolemy, in particular, described in details the stereographic projection in his book The Planisphere. This projection is the basis for all astrolabes. The second period, that I call the popularizers, have seen the publication of the first treatises describing the drawing of an astrolabe and its use. Knowledge spread progressively to the west of the Mediterranean Sea and the south of Europe. The third period sees the birth of astrolabe manufacturers, who are craftsmen as well as scientists. They allowed explorers to bring cheaper and more accurate instruments with them. We can say that the Golden Age spanned from the 10th to the 18th centuries. The astrolabe rapidly became a companion of all scholars and explorers, and symbolized scientific knowledge. In the novel The Name of the Rose by Umberto Eco, adapted as a movie by Jean-Jacques Annaud, the main character, Guillaume de Baskerville, is a Franciscan monk during the Inquisition in 1327. He symbolizes the reason and rational investigation, opposing to the belief of supernatural events and religious dogma. In the movie, we can see him unpacking a planispheric astrolabe and a quadrant astrolabe from his travel bag. In the movie Harry Potter and the Chamber of Secrets, Dumbledore's laboratory is full of old books and scientific instruments, such as armillary spheres and astrolabes. At the beginning of the French comedy-drama movie All Three of Us, a scene shows the Shah of Iran, sitting on his office desk. Behind him, we can quickly see 2 small astrolabes displayed on the chimney. The astrolabe spread during the 12th century in Persia. It was a necessary companion of all leaders and kings in the region from India to the Middle East. Nowadays, the astrolabe is sometimes used as the main subject of stories in novels or comic books. Here, the French comic, Jules Verne et l'Astrolabe d'Uranie, by Carlos Puerta et Esther Gil. Other comic books develop stories around the astrolabe. Famous painters also included astrolabes in their compositions. Here, a painting by Paolo Veronese, Allegory of Navigation with an Astrolabe, dated from 1565. This painting by Jan Bruegel the Elder and Peter Paul Rubens, from 1617, is called Allegory of Sight. It is part of a series on the 5 senses. On the left, we can see several instruments, amongst which, a planispheric astrolabe. Several countries have honored astrolabes or characters related to astrolabes, on postage stamps. Or even on bank notes. Above a banknote from Portugal with a mariner's astrolabe. Below a banknote from Iraq with a planispheric astrolabe. Some even go very far, and tattoo an astrolabe on their skin. It is also possible to create mechanical astrolabes, in the form of a clock or a watch. The reed of the astrolabe rotates on the background plate, at the pace of sidereal time. Needles show the position of the sun and the moon on the ecliptic. Here, the superb mechanical watches, called astrolabium, from Christian van der Klauw. The most famous astronomical clock in the world is in Prague. It is in fact an astrolabe clock. We recognize the ecliptic circle, scaled with zodiac signs, that rotate with time. 2 large needles hold the sun and moon symbols. On the background, the horizon separates the orange from the blue of the sky and unequal hours are drawn on the blue background. Let's now study the planispheric astrolabe. Astrolabe makers have seen, in the planispheric astrolabe, a territory for expression and creativity, and they have progressively created real pieces of art, with rich decorations and finely chiseled and engraved retes. Today, ancient astrolabes are kept in museums or sometimes in private collections. Some fetch high prices in auctions, sometimes topping out at several €100,000. The face of a planispheric astrolabe is composed of several elements, some being mobile. The throne, often richly decorated, allows the user to hold the astrolabe vertically, with a ring and sometimes a cord. The limb is the ring around, thicker than the plate. It is scaled in degrees and hours. The ruler rotates around a central axis. It allows the user to point to a scale mark on the limb or a point on the plate. The plate, on the background, is designed for a given latitude. An astrolabe was usually provided with several plates drawn for different latitudes to cope with different locations. The rete also rotates independently around the axis. It represents the sky rotating around the pole. It has an ecliptic circle, scaled in ecliptic longitude with zodiac symbols. Star pointers show the position of the main stars. The rete of a planispheric astrolabe is in itself a piece of art. It is the element on which astrolabe makers expressed the most of their creativity and skills. The back of an astrolabe has an alidade, which is a rotating pointer that is used to point a star through its two pinholes. The alidade can also point to the calendar on the limb. This calendar gives the ecliptic longitude of the sun in function of the date. The shadow square is an abacus used to measure the height of buildings or landscape elements. Unequal hours separate daytime in 12 hours between sunrise and sunset. Sometimes, other layouts can be found, such as a table of sines and cosines, a curve of the equation of time, or other drawings. The calendar, on the back of the astrolabe, is usually the first thing to consider when using an astrolabe. Knowing the date, we rotate the alidade to that date and read the corresponding ecliptic longitude of the sun. This longitude is then used on the face to rotate the rete. When the curve of the equation is drawn, it provides a direct reading of the value on the scale located on the alidade, depending on the day. The shadow square is used to measure the height of something, or even the depth of a well or a valley. It converts an angle to a value that gives the height, knowing the horizontal distance of the object. It is based on a rule of 3, with a double scale of 10 or 12. The system based on 12 was used in Anglo-Saxon countries. The planispheric astrolabe is based on the stereographic projection. This projection makes it possible to map a sphere on a plane. It is the origin of the name planispheric. The advantage of this projection is the conservation of circles and angles. A point of the sphere is projected on the equatorial plane, seen from the South Pole. A point located in the northern hemisphere will be projected inside the equatorial circle. A point of the southern hemisphere will be projected outside, the farthest from the center, the closer from the South Pole. This is why the layout of an astrolabe is limited to the Tropic of Capricorn. Its circle defines the size of the astrolabe. This is valid for an astrolabe to be used in the northern hemisphere. For an astrolabe of the southern hemisphere, the projection will be done from the North Pole, and the limb will be limited by the circle of the Tropic of Cancer. For a location at a latitude of 50 degrees north, the horizon, which is inclined with respect to the pole axis, is projected as a circle shifted off the axis. Circles of altitude above the horizon are projected as circles that are shifted proportionally to the altitude. These circles are called almucantarats or almucatarats. On the plate, the circle of 0 degrees of altitude defines the horizon. It separates what is above the horizon, here in orange, and what is below. The east horizon is on the left. We need to remember that the celestial sphere is projected on a plane and that we see it from above, as if we were outside the celestial sphere. That explains why the cardinal points are reversed. Altitude circles are drawn above the horizon. They converge towards the zenith point. Azimuth meridians are drawn as arcs passing through the zenith point, here in green. It is also quite common to draw arcs of twilights that correspond to negative altitudes below the horizon. A plate is designed for a given latitude. Before using the astrolabe, the correct plate needs to be installed on the mater. An astrolabe is an assembly of several components around the central axis. The mater is the support on which all elements are added. It is surrounded by the limb and topped by the throne. The plate is inserted inside the mater and fixed with a notch. Then the rete is added so that it can be rotated easily. Then the ruler, also mobile. Then everything is fixed with a pin inserted through the axis. Here are the components of a modern astrolabe made in brass. It was built by Brigitte Alex, in France. Above is the mater, engraved with constellations, which is purely for decoration and has no purpose as the astrolabe function. The plates are below and are engraved on both sides, offering 4 latitudes, 41 degrees, 44 degrees, 47 degrees for Besançon, my hometown, and 50 degrees, which is enough to cover the main latitudes in Central Europe. The rete is finely cut. Above, on the right, the ruler that is placed above the rete. Above, on the left, the alidade, used on the back of the astrolabe. Here a split view of the components, displayed in a museum. The rete has 2 main elements, the ecliptic circle and the star pointers. They represent a simplified sky map that rotates in function of the day and time. The other elements are only decorations and fixtures for the pointers. They also ensure the rete's rigidity. Ancient astrolabes usually had 10 to 20 star pointers, historically 17, for the brightest stars. On an astrolabe drawn by a software, here Shadows Pro, it is possible to draw a more precise sky map with more stars and constellations, as if the rete was transparent. With this representation, it is clear that the sky is drawn inverted, as the celestial sphere is seen from outside, due to the projection. The best way to see nice astrolabes today is to visit museums, such as the Conservatoire des Arts at Métiers in Paris. This large planispheric astrolabe, built by Arsenius in 1569, is in brass and its diameter is 30 centimeters for a weight of 3 kilograms. The History of Sciences Museum, in Oxford, UK, is one of the most fascinating. It displays a large number of sundials and astrolabes, of various types and materials. Here, a collection of small astrolabes, of 8 or 9 centimeters, also in Oxford. This case is displayed at the Galileo History of Science Museum, in Florence, Italy. It contains several tools for surveyors, such as rulers, compass, squares and an astrolabe. This large astrolabe of at least 40 centimeters, from the 16th century, was displayed at the Museum of Confluences, in Lyon, France. The Museum, a museum in Marseille, France, displays 2 nice ancient astrolabes, from a collection owned by the Paris Observatory. On the left, a Moroccan astrolabe from the 18th century. On the right, a Syrian astrolabe from 1326. Astrolabes can also be seen at the Louvre Museum in Paris, at the Science Museum in Geneva, at the Maritime Museum in Greenwich, at the Adler Planetarium in Chicago, and in many other places around the world. Some of these museums can be visited online. From ancient astrolabes or modern replicas in brass, wood or plastic, to computer simulations and drawings, we have the choice. In particular, the Shadows Pro software, well known for the design of sundials, can also draw and animate several types of astrolabes, such as the Mariner's astrolabe, the planispheric astrolabe or the universal astrolabe. Functions of Shadows Pro dedicated to astrolabes will be described in other videos. Meanwhile, you can visit the site www.shadowspro.com to discover additional information on astrolabes. And, on this site, you can also download a free user manual, a genuine book of 140 pages, with many color illustrations, on sundials and astrolabes. This book can also be ordered on paper, printed in colors or black and white, using a print-on-demand service. Shadows can be downloaded from www.shadowspro.com.